Today's lesson is loaded with review from last year, and that should make it very accessible, and it should make it go fairly quick. Of course, I will load it up with extra things that I think are cute, and so I'll drag it out. But please be sure that you do own all of these ideas. We start with our discussion of electric circuits with the symbol for a seat of EMF, and this particularly swirly E being our symbol for a seat of EMF. Of course, you have the short and the long, representing an electric cell. That's of course not the only way to have a seat of EMF, but in the case of an electric cell you have these two different conductive materials, and then there's this space in between where you put an ionic fluid which reacts differentially with these two, causing one of them to become a low potential, the short one, and the other to become a high potential, the long one, and thus chemical energy is transformed into electrical potential energy, and that is what an electric cell does. You put many cells together, and of course you have a battery, but those are turning chemical energy into electric energy. And then there was this other list that I asked you to memorize, where you have a device which turns kinetic energy into electrical potential energy, and light energy into electrical potential energy, and heat energy into electrical potential energy, and this confusion of deformation and pressure being transformed into electrical potential energy. And probably not included in our list last year, but fuel cells. And my understanding of the difference between a fuel cell and an ordinary electric cell is that in a fuel cell the chemicals here get consumed. That seems there would also be chemical reactions in a typical electric cell, but then you can open the gas cap and add more, putting more hydrogen into this, hydrogen and oxygen into the cell, one style of fuel cell. One of you could educate me otherwise, if that's not the case, when we get back into class, about how a fuel cell differs from a normal electric cell. But there are all of these mechanisms for creating electrical potential energy. And then we take that seat of electrical potential energy and we put it into a circuit, a loop, a circus, that is a complete circle and hence a circuit. Now this is a rather complex circuit. It's a multi-loop circuit, and we'll take that on. I mean, we can make them harder than this, but we could certainly make them much easier. But we're going to start with this level of difficulty. And what I'm interested in, given the strength of these seats of EMF and the resistance of these three resistors, what current will be flowing in these three branches of this circuit. Recall that everywhere along this, I'll color it in red. Everywhere along this branch here, it's marbles in a tube, and there cannot be any difference in the current anywhere there. So there's one current that goes everywhere in this red place, and a potentially different current that goes everywhere in the green part, and yet another current that goes everywhere in this pink part. So there would be three currents, and you need to recognize that fact as you set out to work with determining the currents. And I'm going to start by recognizing that there are three currents. I'm going to give them names, very creative names, like 1, 2, and 3. And I'm also going to choose the direction that they are flowing. It could be that I'll get this direction wrong, and the result will be that when I get an answer, it will be negative. Let that be. The other thing that I would like to be very conscious of is that one of the sides of this seat of EMF is the high potential and the other is the low potential. And you need to be very conscious of that the long is the high potential and the short is the low potential. And you'll excuse me a minute while I fix something. Haha, you clever man. You've done it. Okay, so we put the negative with the low potential and the positive with the high potential. Very important to be conscious of that. And then we will apply Kirchhoff's loop rule, which says if you go around any loop and come back where you started from, the sum of the voltage gains and the sum of the voltage losses will be zero. Which makes sense. If you start here, oops, why aren't you working? Ah, there we go. If you start right there and go around and come back to that point, what is the potential difference between where you started and where you ended? And the answer is nada. So, sorry, having a frustrating time here. I will start by going around the top loop, this pink and green loop, and I'm going to go around it clockwise. And the first thing that happens is I go through this 4 ohm resistor with the current, which is a voltage drop. It's like going through the rapids in a river. With the current, you drop as you go through the rapids. I'm going to go through this seat of EMF from the high to the low, so that is a drop of 1 volt. Then I will go through this seat of EMF from the high to the low, so that is also a drop. Uh-oh. Excuse please. That is a drop. Everything is going to be messed up here, of 5 volts. And then I go through this 5 ohm resistor with the current, so it's also a drop of 5 times the current there. Resistance times current gets you that voltage drop. Frustrations are just beginning. We will do the bottom loop clockwise, and it looks like I started right here. So I need to remember that. So when I get back to there, I'm done with the loop. I go through this one against the current, so that will be a gain. And I go through this one from the low to the high side, negative to positive, so that will be a gain of 5 volts. Here it was 5 times I2. Then I go through this one from the low to the high, so that's a gain of 23 volts. And then I go through this one with the current, so that's a drop of 6 I3. Please note, you go through a resistor against the current, it's a gain. You go through a resistor with the current, it's a drop. You go through a seat of EMF from low to high, you have gained. And if you go through it from high to low, you have dropped. I guess the same sort of thing could have been done with a resistor. If we presume that the current is going this way, then this must be the high potential side of that resistor and this the low potential. And so if you go through it against, you are going from negative to positive, a gain. If you go through a resistor with the current, you're going from positive to negative, a drop. Okay. We get 2 equations from loops, and then we stop. And the last equation we will get using Kirchhoff's junction rule. We choose one of these 2 junctions. I choose this one over here where the green current and the red current and the pink current come together. And it must be that there's as much current flowing into that junction as coming out. That if I take this, which is a negative current coming out, and this one, which were positive currents going in, those three must add up to 0. Or if you like, I2 going in and I3 going in must equal I1 coming out. Then we take these three equations with the three unknowns, I1, I2, and I3, and solve them simultaneously. And I taught you last year to do that using matrices. If you have a calculator that solves equations for you, that's really too bad because of the laziness you will develop, but there is no penalty for your using it. This equation here is going to be negative 4 I1, negative 5 I2, 0 I3s, and then this is negative 6. I move it to the other side of the equation, and in just a minute it's going to say positive 6. Okay, that's important. We want to move this negative 6 over to the other side of the equals and then put it into this matrix. This equation here has no I1s. It has 5 I2s, negative 6 I3s, and this is 28, but move it to the other side of the equals, so we write a negative 28, and this one here is negative 1, positive 1, positive 1, and a 0 on the other side of the equals. Then you can put this into your calculator and do reduced row echelon form on this matrix. And those of you who didn't take plus physics last year, somebody's going to have to hold your hand and show you how to do that. And that person could be me. Oh, yucky, Mr. Houghton's going to hold my hand. If you do the reduced row echelon form of this, there is row echelon form. You should see this matrix and then these numbers here. And so we can just read this, that current 1 would be equal to 1 amp, and current 2 would be equal to negative 2 amps, and current 3 would be equal to 3 amps. Notice a negative value. That means that in fact this current would have been flowing the opposite direction. That this 23 volts was such a bully that it got its way and made current flow that way, but it forced both of these currents to flow against. Not true, it wasn't against here. So both of these two currents would flow to the right. You ought to be trying this out on your calculator. I'm going to try it out and make sure that this matrix here, reduced row echelon form, does give that result. I sure hope it does. But you ought to be testing your ability to do these because you will have to do them for homework and you're going to have to do them in a lab. And those of you who are completely at a loss, you just pay very, very close attention in class and you say, explain it again, Mr. Houghton, and don't stop explaining until I understand. Next topic, which is again a repeat from last year if you took plus physics, is terminal voltage. That you have this electric cell has chemicals inside that make it be a seat of EMF, but it is also true that when this is in a circuit, current is going to flow through this, and that current is going to encounter some resistance to moving through the cell. So to physically represent the cell, you have the chemical behavior, which is a seat of EMF, but also inside of that seat of EMF you have what we call an internal resistance. We use a lowercase r. And then we have these 2 points, A and B, which are the terminals, the outside edges. And so when we refer to the terminal voltage, I want to know the voltage between the two edges, which would include both a voltage from this seat of EMF, but also a voltage, possibly a drop, from this internal resistance. that if the current flows through in this direction, then the terminal voltage VAB, the voltage between A and B, would be equal to the EMF minus the current times the internal resistance. Notice I've just done a Kirchhoff. I started here and I had a voltage gain, and then because I went through this with the current, a voltage drop. But there is a very good likelihood, excuse me while I get rid of likelihoods, there is a very good likelihood that you will at some point run into this thing with the current flowing that way. And if you Kirchhoff with the current flowing that way, the potential difference from A to B, as you go from A to B, you would have a gain as you went across the seat of EMF and a gain as you went through the resistor. And so the terminal voltage would be bigger than the EMF with the current flowing in the direction that you would expect it to. This is the positive end. It ought to be flowing away from the positive. Then you have an internal voltage drop. But you could have an internal voltage gain if the current was flowing the other way. Very quick topic that you probably don't even feel the need for, but we've already dealt with capacitors in series and parallel, and then the book finally gets to resistors in series and parallel. And these three, I hope you would recognize, are in series, and the for that sort of a situation, the thing which is the same for all of them is going to be the current. And so the equivalent current is equal to each of the individual currents that you have there. Oh, should use the lowercase I, shouldn't I? Each of these currents, I1, I2, or I3, is going to be equal to the equivalent current. And the voltage drop is going to, the equivalent voltage drop is going to be the sum of this voltage drop plus that voltage drop plus that voltage drop. Very Kirchhoff. And so you have the equivalent voltage is equal to the sum of the individual voltages, and that I does not mean current, it means which one of these voltages, and then I can pull on this thing. Oh, there we go. And so the equivalent current times the equivalent resistance, which would be the equivalent voltage drop, is equal to the sum of the equivalent. But of course the I's are all the same, so that falls away, and you have that result, that the equivalent resistance here would be the sum of these three resistances. Woo! What a lot of work for nothing! And then if you put the resistors together in series, it is of course the case that they all have the same voltage drop, but that the equivalent current flowing through here would be the sum of the currents through each of the individual ones. Again, uppercase I for current, lowercase I for which one, and then I replace I equivalent by V equivalent divided by R equivalent. Mr. Horton! R equivalent, and this is equal to VI divided by RI, and so we end up with the reciprocal of the equivalent resistance equal to the sum of the reciprocals of the individual resistances for parallel resistors. Forget it not. Next, the cuteness that will make you get old and gray as you wait, but I think it really is. This is an electric eel, and along the sides of its body are what are called electroplaques, which generate a potential difference across each of these. I think it's about 0.15 volts is generated across each of these, just like the nerves in your body are a matter of building up a potential. I'm not sure how big. These are nerve cells which have been evolved to produce a fairly large voltage, 0.15 volts, but there are like 5,000 of them down the length of the eel's body. So it produces the equivalent of 750 volts between the eel's nose and the eel's tail, which is sufficient to cause a current of almost 1 amp in the water here. And when the fish swimming nearby have that shock go through their bodies, it stuns them, perhaps it even kills them. 1 amp is a lot, and then the eel gobbles them up. But the question is, if the fish are being stunned by a current of 1 amp, this eel's in the bathtub too. Why isn't it shocked by that 1 amp? And that, I thought, was a very, very neat question. And here's the tedious resolution. That here you have a series of electroplaques, each one generating 0.15 volts, but having a resistance to the movement of current, an internal resistance of 0.25 ohms. There are 5,000 of them in each of these rows and 140 such rows going down the eel's body. The resistance of water from the eel's nose to its tail is about 800 ohms. So there you've got the circuit. We'll simplify that circuit by adding these together, and I'll add the voltages together. 5,000 times 0.15 is 750 volts, and I'll add all the internal resistance together. 5,000 of those is 1,250 ohms. You have 140 of those, and the voltage is 750, but I need to add up all of these resistors in parallel, and that's 140 of them, each with 1,250 ohms, and that comes to 0.112, but we need to take the reciprocal of that, so the equivalent resistance from the head to the nose of the eel is about 9 ohms. And if we then go back to our circuit, we have a potential difference of 750 volts, and together with the 800 in the water and the 9 of the eel, we have this resistance. And you look at that and you can see that the current that's going to flow is going to be the voltage divided by the resistance, almost 1 amp, but that's an equivalent of 1 amp flowing here. Through each of those 140 pathways, there's only going to be about 7/1000ths of an amp. So there is the trick. The eel does have almost 1 amp flowing through its body, but by 140 different pathways. And so the eel does not suffer the damage that the fish do. Very cool, Mr. Eel. You have done it. Thank you for your time.